All right, 17a, let's do some limits. So here is a limit we're going to see kind of a lot in the future. It's an indeterminate 0 over 0 type, meaning if I plugged in x equal to 3, I would get 9 minus 9 on top, which is 0, and 9 plus 3, which is 12 minus 12 on the bottom, which is also 0. And so when we're trying to evaluate a limit like this, what we often have to do is some algebra, which often involves either factoring or multiplying by a conjugate or using a common denominator. In this case, we're going to factor. Usually there's factoring involved in kind of all of them, even if we have to do some of the other steps first. So I'm going to factor the top and the bottom. This is going to be the limit as x goes to 3. The top factors as x minus 3 times x plus 3. The denominator factors as x minus 3 times x plus 4. And then we can see that those x minus 3's can cancel out. Now here's the thing, and this is an important thing about a limit. The limit as x approaches 3 is asking what is this function doing as x gets closer and closer to 3, but not actually equal to 3. So when I ask what's the limit as x approaches 3 of this, it's actually the same as the limit as x approaches 3 of this remaining result, because canceling this out over here doesn't make a difference if you're looking at everything where x is not equal to 3. So I get the limit as x goes to 3 of x plus 3 over x plus 4. What I'm saying there, just to kind of clarify that even more, what I'm really saying is these two functions, x squared minus 9 over x squared plus x minus 12, and x plus 3 over x plus 4, these are the same everywhere except at positive 3. Right? Here when I plug in 3, I get 6 over 7. Here when I plug in 3, I get 0 over 0. But here's the thing I'm trying to emphasize. When we're taking the limit as x approaches 3, we don't actually care what's happening at 3. So for all intents and purposes, this function and this function are the same everywhere they need to be, which means that the limit of this and the limit of this also get to be the same because these functions are the same everywhere close to 3, just not at 3. So then we just do what's called the evaluation theorem. We evaluate this limit by plugging in 3 for x, and we get 3 plus 3 over 3 plus 4, which is 6 over 7. Notice that once I've actually plugged in the values, I no longer write the limit, but up until then I do. All right, so here's the next one. I want you to pause your video and try this one on your own. Its limit as x approaches negative 5 of 4x plus 20 over x cubed plus 125, and yes, it is a 0 over 0 type. So pause your video, give it a try, and then once you're done, start it up again, and I'll show you the solution. So here's the solution. The bottom does factor kind of in a challenging way, with the limit as x goes to negative 5. The top, we can obviously factor out a 4. And we're left with x plus 5. And the x plus 5 is the factor we want to cancel because it's going to 0. The denominator, x cubed plus 125. Well, x cubed plus 5 cubed is of the form a cubed plus b cubed. And the sum of cubes factors as a plus b times a squared minus ab plus b squared. There's this thing called SOAP for same, opposite, always positive. Right? This sign is a plus b, this sign is the same sign plus, this sign is the opposite sign, this sign is always positive. It also works if it's a cubed minus b cubed, except the opposite changes. So x cubed plus 5 cubed is going to factor as x plus 5 times x squared minus 5x plus 5 squared. These can cancel. We're left with the limit as x approaches negative 5 of 4 over x squared minus 5x plus 25. And then we can plug in the remaining, or plug in x equal to negative 5 and get 4 over negative 5 squared minus 5 times negative 5 plus 25, which is equal to 4 over 25 plus 25 plus 25, which is 4 over 75. So there is a couple examples of 0 over 0 limits where you have to factor and cancel stuff.